Well, good afternoon. It's 2:38 on Wednesday, the 15th of January, 2020. This is supposed to be differential equations, but the trouble, and we're 8 minutes late getting started, but I've been waiting for someone to show up, went down to the restroom, various things, met with a student or two, and still nobody's here, so we're going to go and get started. I wish y'all were here. I'll wait and do the announcements until we get some people in. I'm not seem to be able to get the slide to open. There it goes. Okay. Last time when we met, we went through the syllabus. We went through my locator card. We went through the research paper instructions, how to get to YouTube video, how to access your website, class key, some of the links that I put on the email, Blackboard, went over the new Blackboard, and we did get started in Chapter 1. We didn't get very far. Chapter 1 is Introduction to Differential Equations, and we started in 1.1, which is Definitions and Terminology, and we talked about classifying differential equations. There's 3 different ways we do it: by type, by order, and linearity. Okay. And we went over last time what the 2 types are. They're either ordinary differential equations or partial differential equations. In this text, we're only going to be solving ordinary differential equations, ODEs. We may do some things with partial derivatives. Yeah, that's okay, but we're not solving any partial differential equations. And that led us to example 1, bottom of page 3. So let's go on and list those here. And what we have, let me get my pen set up. Okay. dy dx plus 5y is equal to e to the x. Okay. Now, all we're interested in here is what type of differential equations these are. And we got our first student. Way to go. Today's the 15th. Good, thanks. How about you? All right. And let me pause for a moment here and turn on the projector, flip the lights. Now, I can't remember if I read these announcements to you before the transfer days in February. No, okay. Let's go through these quickly. Here are the announcements. The Lawson State Community College Transfer Fair Days, got an awful long title here, 2020, will be about 3 or 4 weeks away. Wednesday, February 12th, 2020. I think that is exactly 4 weeks away from today. Only it was 9:30 to 11:30 in the morning. So just short of 4 weeks away today, because it's in the morning. This is on the Birmingham West Campus. That's the academic building, which is B Hall. And that's a long hallway, and they set up tables all up and down the hallway. Then on Thursday, February 13th, 4 weeks from tomorrow, again from 9:30 to 11:30, they'll set up on this campus, and my best guess is they'll be in the faculty staff dining room, which is just next to the cafeteria. They say here campus cafeteria in building A, which both of them, the faculty staff dining room and the cafeteria here in this building, but because that goes from the latter part of breakfast to the first part of lunch, campus cafeteria is not probably the best place for that. I think it'll be next door in the faculty staff dining room. Okay, here are some of the institutions who have been invited to attend. No guarantee they'll be here or even both days or whatever, but here are what they are. AUM, Mississippi State, University of Alabama, Montevallo, Alabama State, Alabama A&M, University of West Georgia, Auburn University, Jacksonville State University, Stillman College, William Carey University, they listed Alabama twice, okay, UAB, UAH, University of West Alabama, Troy University, South Alabama, then even though they listed University of Alabama twice, this one is the third time, but this is University of Alabama College of Continuing Studies. So that's a separate, they'll be here on two tables. Athens State, and then UAB was listed, but also UAB School of Health Professions will be here. North Alabama, Stanford University, Alcorn State, Kentucky State, Tennessee State, Faulkner University, Southeastern Bible College, Talladega College, and Georgia Southwestern State University. A bunch of them. 4 weeks from today and tomorrow. All right, now this came from a guy who is at University of Illinois. His name is probably Dr. Joseph Muskin. He's running a summer research program for the Center for Power Optimization of Electrothermal Systems. That spells POETS. Okay, you would think a physics thing would be named POET, or engineering thing would be named POETS, but it is. We are looking to recruit minority engineering students to work at 3 of our 4 institutions this summer at University of Illinois, University of Arkansas, and Howard University. It's a 10-week internship that exposes undergraduates to academic research in the fields of mechanical, electrical, and material engineering. The students are paid $5,000 stipend to go for 10 weeks. That's $500 a week to go and learn stuff, okay? But not only that, you receive free housing. Now, I think at most of the schools, what that includes is free meals, because the housing comes with meals. You receive your airfare there and back one time. They don't fly you back every weekend or anything, but they do fly you out there once and back home once. And you also gain access to weekly professional development webinars, as well as other benefits. I have a brochure here. You're certainly welcome to look at it. Now, note this brochure, I sort of pieced it together with 2 pieces of paper, so you can take a look at that if you're interested. And there's more on the email that they sent. It's a lot of information, a lot of good stuff. It sounds like a great program. So here it is if you want to look at it. All right, I got marked you here, and I was just getting started, or where we left off last time, example 1, bottom of the page 3, section, chapter 1, Introduction to Differential Equations, 1.1, Definition and Terminology. And we had just said there were 3 ways that we're going to be classifying differential equations: type, order, and linearity. We've stated how we do it by type. There's only 2 types: ordinary differential equations, partial differential equations. This course only deals with ordinary differential equations. Now, we may also be taking partial derivatives. We will be taking partial derivatives when we're analyzing some ordinary differential equations, but we're not solving partial differential equations. We're just dealing with partial derivatives. And here is the first equation they give. Now the question is this ordinary or partial? Ordinary. Anytime you see the d's as d's, then those are your ordinary differential equations. I had an older guy in my class last term, and he called this other type of a D a curly D. Okay, I hadn't heard that before, but that's what he called it. Maybe it's pretty common. I hadn't heard it. And if it's a curly D, that's a partial differential equation. We're not doing those as term, but we'll show you what they look like. How about this one? D2y dx squared minus dy dx plus 6y equals 0. Ordinary or partial? Ordinary. Okay, okay. I'm real tempted to say a few more things. I'll say them in a minute. Okay? dx dt plus dy dt equal 2x plus y. Ordinary or partial? Ordinary. Well, this one, I'm not going to call it out, it would give it away. What's that one? That's a partial. Both of those are partial. That's read second partial of u with respect to x squared plus the second partial of u with respect to y squared equals 0. Obviously a partial differential equation. We're not doing any of those this term, okay? That's usually a senior to graduate level math course. I had it as a senior when I was at Georgia Tech. All right, how about this one? Nope, wrote it wrong. Nope, wrote it wrong again. They're mixing this up on me. Yuck. Okay. How about that one? Partial, of course. And okay, that one, partial. Okay. Now, shouldn't be jumping ahead like this because I don't like writing these things down several times. These are classified according to type. Ordinary differential equation, partial differential equation. The next kind is order. Order is what you might say, the degree of the differential or derivative. What would this be? First order. This one? Second order. This one? It's still first. The maximum is first. So it's first order. This, if we had done these would be second, first. Okay. Now, the third type is linearity. We won't be able to do all these about that, but what linearity means is that none of the derivatives or none of the functions y are anything other than in linear form. In other words, this can't be squared or square root or multiplied by another derivative. That would not be linear. The y here cannot be squared, square root, cube root, or multiplied by some other y, some other form of y. Okay? So this would be a linear form. First power, first power. Doesn't matter what the right-hand side does, the functions of x, that doesn't matter. Okay? This would be linear. Second order, ordinary, linear, because this is to the first power, that's to the first power, that's to the first power. Okay? Now, this is also ordinary, first order, and that is linear. What makes it look better at being linear if you move the y on this side, but minus y is equal to 2x. Then it's pretty obviously linear. Okay? Now, we don't use those terminologies, or not much, in terms of partials, but these would all be linear, okay? Because you're not raising a derivative to any power or multiplying a derivative by a function of y, okay? So that would be the cases there. So I actually cheated a little bit and got into the other two, and I just hit the wrong button, okay? Now, before we get to order and linearity, here's another little note, okay? Throughout this text, ordinary derivatives will be written by using either the Leibniz notation, okay, Leibniz notation, and that would be of this form: dy dx d2y dx squared d3y dy cubed dx cubed, or so on, okay? Or we will use the prime notation, okay? Now the prime notation for this one would be y prime, this would be y double prime, this would be y triple prime, okay? So either one of those notations. Now, and here's this. I made a couple of announcements. If you listen to the first part of the UT, you'll hear them. And also what we've covered so far. We're in Chapter 1, Introduction to Differential Equations, 1.1, which is definitions and terminology, and here we're hitting some more definition terminology. Just we're mentioning, in this text, we'll refer to, we're only going to deal with ordinary differential equations. That's when you have the d's here, okay? Now down here in prime notation, you might say, how can I tell whether that's ordinary or partial? Partials are never written with primes. So if you see a prime, that's ordinary. Now these have the same meanings, okay? And let me go over at least one issue, okay? In this one, in this notation, Leibniz notation, the variable on top is the dependent variable, the variable in the denominator is the independent variable. In prime notation, you can tell what the dependent variable is, you can't tell what the independent. You can't tell if this is derivative of y with respect to x, with respect to t, with respect to any other variable. You just don't know. So there's one advantage to the Leibniz notation. But this is far easier to write. Okay? The primes are so much easier to deal with. Okay.
I took we used to use the prime notation for partials. So you're like a subscript, like with the prime, with like, for instance, if it was the derivative of the function y with respect to x, they're like a subscript. So
Yes. You see, that's why I said the primes aren't done. What they do is a subscript then. Yeah. The partials are given subscripts, not primes. Yeah. Primes are superscripts, these are subscripts. And then there'll be the letter that you're taking respect to. You're absolutely right. Okay, the variable you're taking respect to. Now, the advantage of the prime notation, it really is easier to read, easier to write. Here's some examples of that. Y prime plus 5y equal e to the x. So easy to write. Okay? Another one, y double prime minus y prime plus 6y is equal to 0. Okay? Very easy to write. Now, here's a limitation, another limitation of the prime set. You can only write primes for the first three derivatives. After that, you put numbers in parentheses. So the fourth derivative is not 4 tick marks. After a while, you just can't count the tick marks. They're hard to do. The next one will be y4 in parentheses. Why in parentheses? You don't think it's a power. So if it's in parentheses, that's a derivative. If it's not in parentheses, that's the power. That would be y to the fourth power. Okay. So keep that in mind. Anything up to 3 or primes beyond 3 are numbers in parentheses. Okay. Now, we're not going to do too much with this, but you could, and that would be an unknown derivative, as in somewhere up there, okay? d n y dx to the n. That's the nth derivative, whatever number n stands for. In prime notation, since you don't know, it could be a 1, 2, or 3, you just don't know, so you usually write that as y in parentheses to the nth, okay? Because usually it's higher than 4, but it doesn't have to. Okay. Now, they're talking about what I've already mentioned, but let me give their example. d2x dt squared, okay, plus 16x is equal to 0. All right. Now, and again, Leibniz notation allows this. Prime notation is not always clear. X is the dependent variable. T is the independent variable. Okay? Now, a lot of times, this is perfectly legal, but a lot of times they like to have, in fact, this is completely right. All the terms with the dependent variable on one side, and any terms that don't contain the dependent variable only have the independent variable, they'll usually be on the other side. It's not always, it doesn't have to be that way, but that's usually how they do it. Okay? Now, there was, of course you know, that Newton came up with one of the first, well, many people say he came up with calculus first. There was a lot of dispute because Leibniz actually published some calculus before Newton did. But Newton swore that he had stolen his ideas and then rushed to publish. And Newton was sort of a strange character. He was a perfectionist. He hated criticism. So therefore, until he was certain he had all the bugs worked out, he wasn't going to publish it. Leibniz, he'd kick it on out there and publish it, and then later find out, whoops, I made a mistake, and then go back and retract and redo it and stuff. Very different personalities and very big arguments between them. Okay. So, but Newton came up with another notation, and they say its title was the dot notation. And some people call it the fly speck notation. Like if the fly had left a mark on your paper, you wouldn't know whether it's a calculus notation or differential notation or not. So here's the key. Now, the other thing is Newton was dealing mostly with physics, okay? And a lot of what he dealt with were derivatives with respect to time. Velocities, accelerations, and so on. So he used one set of notation for time and something else for anything that wasn't dealing with time. So for instance, this is a very standard physics type notation. d2s dt squared. Newton would not have said that. Okay? Well, wait, I'm sorry. Is equal to minus 32. Okay? Now, writing that in Newton's dot notation, some people call it the fly speck notation, this would be S with 2 dots over it is equal to minus 32. Okay? Now, The dots mean with respect to time, the prime means with respect to another variable. Okay? So it doesn't quite look the same because the dots are put over the independent variable, dependent variable. The primes are put slightly superscripted to the right. Okay. Now, and then as Keeston has already pointed out, there is also one other notation, and that's when you're dealing with partial derivatives. You would use a subscript notation, which would be something like this: u sub xx equal u sub tt minus, I lost my place, minus 2u to the t. Okay. Got lost in the sauce there. Okay. Second.
What did you just write?
Okay. It's u sub xx equal u sub tt minus u sub t. Okay. What in the world does that mean? These are partial derivatives. The second partial of u with respect to x squared is equal to the second partial of u with respect to t squared minus 2 times the partial of u with respect to t. That's the other notation, which is subscript notation, which is used only for partial derivatives. We're not doing, we may take some partial derivatives, but we're not doing partial differential equations. Yeah, well, we're going to hit them, so get used to them. Okay. Now, let's move now. See, we were doing classification according to type, and then we got off into all these other ways to write these types. Let's go back to our classification, this time with respect to order. All right, to erase these? Okay. All right. The order of a differential equation, either ordinary or partial, is the order of the highest derivative in the equation. Okay? So d2y dx squared plus 5 dy dx cubed minus, that's a cube there, I can't write, minus 4y is equal to e to the x. Okay, sorry. Have to look across the page. Sometimes it's easy to lose my terms. All right. First thing, what is the type of differential equation this is? Ordinary, okay? There's no partials in this. Okay, what's the order of this differential equation? Yes, you're right. Second derivative. This is a cube of a first derivative. That doesn't change the order. The order is the maximum derivative taken. This is still a first derivative, you just cube it. And this is y to the no derivative, just the function y. Okay. Now, based on what I told you before, what would be the linearity of this? Linear or not? No. Because of that cube there. Remember, your every derivative and function, dependent variable, has to be just to the first power. That's to the third power. Second order, nonlinear. Okay. We haven't gotten to the nonlinear part, but I thought, why waste an example? Okay. Now, there will be at least one type of differential equations which will show up in, see, all these that we've shown so far are really derivative equations because they show up as derivatives. But we always call them differential equations but truly a differential equation would be something like this. M of xy dx plus n of xy dy is equal to 0. Okay. Now, in this equation, it's obvious. What's your independent variable? What's your dependent variable? And this one on top. Y is dependent, X is independent. Down here, not clear at all. In fact, they kind of both act sort of independently. Okay? You can rearrange and order it so it can be Y as a function of X or X as a function of Y. But one of the keys here is your coefficient functions are functions of both variables. That one and this one. Now, they don't have to be, but when they are, you're almost better to write in differential form. Because there are certain techniques that we're going to use to solve this equation that won't work on any of the others. And the other things we use on the others won't work on this one most of the time. Okay. So let's move to example 2. I think I'll erase what we got here. Oh, and by the way, I may have said this last time, but it really pertains to Wednesdays. On every Wednesday, let me back up. Every Monday class, when this class is over, I'm through for the rest of the day of teaching. I'm here till 6, but I'm in office hours. So if y'all don't stop me, I keep on trucking, okay? So please, because my watch, the battery died, I haven't had a chance to get it fixed yet. So, if so Wednesday, that's where I was. On Wednesdays, however, Mondays after 3:45, I'm here till 6. So, like I said, if you don't stop me, I'll keep on going. However, on Wednesdays, please stop me by 3:45. The reason for that is I've got a class on the Birmingham East Campus that starts at 4:30. And that gives me 45 minutes. Well, in that 45 minutes, I've got to shut down everything here, go down to my office, swap out books and things like this, and do a few things I forgot to do today, and then book it to the other campus. And sometimes it's hard to get there in 30 minutes. Other times I can, okay? So please stop me by 3:45 because it's going to take me pretty close to 15 minutes to shut everything down and get everything exchanged. I need to be leaving this campus by 4 o'clock. So it's sort of pushing it, so please let me know. But Mondays, we can stay and talk as late as we want to. Okay. Wednesdays, however, I've got to end at 3:45. Okay. Now, example 2. If we assume that y is a dependent variable in the first order ordinary differential equation, then recall from calculus that the differential dy, this is, okay, I'll write most of this down. Here we're going to assume, I don't like to write that y is the dependent variable. Okay. In a first order differential equation. Now, I hope I don't confuse you sometime, but sometimes I get to talking too fast and may slur words, and it's hard to do. That's a first order ordinary differential equation. It almost sounds like I'm being repetitive, but the first word is ordinary, and the second word is, no, the first word is order, and the second word is ordinary, okay? They are not related at all, okay? They just sound alike. It's a first order ordinary differential equation, okay? Now, if that's the case, you could have written this as dy dx is equal to anything, whatever it happened to be. I'm going to write down something that looks absolutely redundant, okay, because the book is doing it. That's why I almost hesitate and say, let's just skip this, but in case you need it, dy dx is the same as y prime, right? That's what we're talking about, notations. Dy dx is Leibniz notation, y prime is Leibniz, is prime notation, okay. Now, if that's the case, this is also true. Written in differential form, this is dy is equal to y prime dx. Okay. This is derivative form, but it is a differential equation. This is differential form of a differential equation. When you separate the d's, dy and dx. Now, how you tell that y is the independent variable? It's the y prime here. But if you just had a mixture of things like we did in that last, or one of the last examples, m of xy dy plus n of xy dx equals 0 or something like that, you can't tell which is more important, which is independent, which is dependent. This one, yeah, you can because of the y prime, but most of the time we can't. Okay. Now,
so the numerator is always dependent?
Yeah, when you have the derivative form, the numerator is dependent and the denominator is independent. Right. So let's do example 2a. I think I'll close this and start a new slide. Here is an equation in differential form. Y minus x dx plus 4x dy is equal to 0. I got lost where I was there. Okay. Now, can you tell which is dependent, which is independent? No. You just can't tell. Okay? Now, if you wanted to force one of them to be, for instance, y to be dependent and x to be independent, here's how you proceed with that. Okay? Divide both sides of the equation by dx. Okay? That sort of eliminates it there, and you have y minus x plus 4x dy dx is equal to 0. Excuse me. Now, you have forced this for y to be dependent and x independent because of just what you said. You have the numerator is y, the denominator is x. Now, this is an okay form. It's a first order ordinary differential equation. Okay. Now, the question you may have, is it linear? And there's a few things that make it a little murky here, but it turns out it is linear. You can have functions of x as your coefficient functions, and you can have x's by themselves. and y's by themselves. As long as this y is multiplied by another derivative or raised to some power, this isn't raised to any power other than 1, this would be a linear differential equation. Okay? But we haven't even gotten there yet, but I just wanted to point that out. Now, they rewrote this, and there's a reason for this, as 4x dy dx plus y, that takes care of this term, and that term is equal to x, and that takes care of this term. You moved it to the other side. Now, this rendition makes it a lot more obvious that it is linear. You can have a coefficient of your independent variable times the dy dx, and that implies y is dependent on x. And then the y is here, so you get all your y's on this side, and all the terms with no y's on that side, that is your x, and that's perfectly fine. Later, we will sometimes divide all the terms by this 4x, okay? And that would leave dy dx plus y is equal to x. And what I was going to say is divide by either 4x or x. And if you did that, then you move your x dependence from here to there. And there will be certain forms that we use, you prefer it there than here. We'll talk about that later. But by doing that, you also remove the x from this side, because then you would just have 1/4. And that's fine. It's just a number. Okay. Now, on the other hand, sometimes you want to get it in differential form. So here's a differential equation in derivative form. 6xy dy dx plus x squared plus y squared is equal to 0. Okay, I'm looking on two different lines out. Okay, so we're okay. Now, what if we wanted to write that in differential form, not in derivative form? Now, this is in derivative form. It's an ordinary, first order, non-linear, because that y is to a power other than 1, differential equation. Okay? So, if we want to write it in differential form, what would we do? You're absolutely right. That would be 6xy dy, usually you put these in parentheses, plus x squared plus y squared dx is equal to 0. That is a differential equation in differential form. So it's the very same equation, but it's in differential form. I think that's all we need to say about that. Except yeah, okay, it's fine. They rearranged the terms. Okay, I was trying to think what they did. They put this on the other side. So they wrote it as x squared plus y squared dx plus 6xy, this is what was throwing me, dy is equal to 0. Okay. It doesn't matter what order you write it. Okay? Now, Here we're going to get to what I consider almost a little picky stuff. Though we're going to be using it, so it's going to be pretty important to pick on it, okay? Here we're going to express an nth order ordinary differential equation, okay, in one dependent variable, okay? And we're going to name this function capital F is a function of x, y prime, sorry, my writing is getting a little sloppy here, y prime, and we are going to let this keep on growing up to and including the nth derivative of y, okay? All right. That's an nth order. Now, remember what order was? Which is your maximum derivative? This is going up to the nth order. Nth order ordinary, because you don't use prime notation if you're using partial derivative. So nth order ordinary. Now, it's not completely obvious whether this could be linear or not. It may not be, okay? But most of the time they will have them be linear. But it's impossible to tell from that notation. Now, that's kind of a weird notation. This is saying all the dependence on x, all the dependence on y, and all the dependence on every one of your derivatives is all on one side of the equation. Therefore, leaving on the other side is 0. Now, I have seen and heard of people dealing with functions and I don't think it's a good idea to leave stop something in the middle of a presentation and not let you know what kind of function you're dealing with. When you have everything on one side and 0 on the other side, quite often that's called a non-homogeneous or non-homogeneous, a homogeneous or homogeneous differential equation. So all the variations on one side, 0 on the other side. Okay. Now, that's a real valued function of n plus 2 variables. Now, how do you get that? Well, obviously the x is a variable and the y is a variable. But then they're treating this as if each derivative is also a variable. So you have y to the first power, second, third, fourth, fifth, up to the nth power. So that gives you n variables there. One more is n plus 1, and one more is n plus 2. So this would be an nth order ordinary differential equation with n plus 2 variables. Okay? Now, that seems a little bizarre. Okay? Now, what if you rearrange this ever so slightly? Okay? Remember this term here? That's the nth derivative of that. You could have written this as dny dx to the nth. Okay? Let me make sure. Yeah. Okay? Now, why they mix up the notations, I'm not sure, but they do. Okay? Now, if you can isolate that nth derivative, say it only shows up in a few terms and you can group all those together, factor out this, and then deal with that, Then you come up with a new function. Same meaning as this function, but isolate this to one side of the equation, put everything else on the other side. Then you have a related function, but it's little f. This is just the way they name it. If you pull out the maximum derivative, okay, then this would produce a new equation, dny dx to the nth would be some new equation, little f, somewhat loosely related to the other one, and that would be a function of your x, your y prime, your y double prime, up to and including y sub n minus 1, the n minus first derivative of y, okay? When you group everything together and the whole function's over here, 0 on that side, we usually use the capital F or G or whatever symbol we want to use. If you pull out the maximum derivative term from this and then write everything else in terms of the remaining variables, this one, this one, this one, all the ones up to, but not this one. This one's over here, so you go up to the n minus first derivative there. There's enough of a connection here, nothing obvious or anything, but this little f is in some way related to the big F. This is when everything is homogeneous. This is when you've isolated the maximum derivative, maximum order of your derivative. We'll see that a little bit later and it'll have more meaning. Okay? This one's called, for some reason, the normal form. Okay? Okay. Okay. So, this is a really nebulous statement here. Thus, when it suits our purposes, we'll use the normal forms. Okay? If it doesn't, we won't. But if it does, so a normal form would be dy dx is equal to some function of x and y. Okay? Why? Because this is a first order here. The maximum order you can have here is a 0 order, which means no derivatives at all, just the function y. So that will be like that. If your maximum derivative was a second order, d to y dx squared is equal to some function of x, y, and in this case, y prime. Because you see, you go up to the maximum on this one. So the maximum's over here. So this is second order, ordinary differential equation. You can't tell anything about linearity on this one, not by just looking at that notation. All right. So let's do example 3. Oh, my goodness. My eyes are so dry. And by Wednesday afternoon, I'm usually running out of steam. Thursday is drug in all day long. But let's see if we can pull through. All right. Example 3, there's an A and B part. I'll tell you now, the B part has an error in it. But let's do with the A part, it's fine. By solving for the derivative, okay, we'll do this. 4x dy dx plus y is equal to x. All right. the way this is stated here, this is what kind of, how we would classify this equation. What type? Ordinary. What order? First order. And it sure looks like it's linear. And it is. We haven't even gotten there yet, but it is linear. Now, what if we wanted to write this in what they call normal form? You isolate the maximum derivative, and just the maximum derivative. No coefficients with it. So you isolate this. So how would you do that? What would be your first step? Yes, subtract y from both sides. Okay. That wipes them out here, and do what? Divide by 4x. Now this is written a little sloppily, but see, these go away, and now you have dy dx is equal to, because that went to 0, x minus y, I can't write, 4x, y over 4x. All right. Now, perfectly fine. It still happens to be everything we said. But this is in normal form. And in normal form, we're not usually trying to distinguish whether it's linear or nonlinear. It's still linear, but it just is a different form. But you see, now this dy dx is a function of x and y. And that's all. Okay? And that's what we saw before. Okay. Now, there's another way to write this. Oh, I messed something up. Whoa. No? Yes, I did. Sorry about that. I got this on two different lines. This is x over 4x, minus y over 4x, because you divided everything. I didn't bring down my x here. I should have. Okay. So this is dy dx is equal to 1/4 minus y over 4x. Okay. And again, this is a function of x and y only. Okay. Let me make sure I've now got this right. Okay. Or, there's yet another way you could write this, and this is how they chose to. If you want the least common denominators like this, then what you could leave it as is x minus y over 4x. And that's how they actually left it. X minus y over 4x. It doesn't matter. All these are functions of x and y, x and y, x and y. Now, the b part, I have a problem. Okay? They've got something wrong here, and I don't know which way it is. Here's a second order ordinary differential equation. Y double prime minus y prime plus 6 is equal to 0. Perfectly good ordinary differential equation. It says write this in its normal form. So what would you do? Isolate the maximum derivative, which is there. So y double prime would equal y prime minus 6, right? Add y prime to both sides, subtract 6 to both sides, you got it. Okay? Now, here's the problem. If you look in the book, they write this as 6y. It can't be, okay? For that to be a 6y, it would have to be a 6y up there. For that to be a 6, it has to be a minus 6 down here. I don't know which way they meant it, okay? it doesn't really matter. And just because you don't have a y in that term or a y prime or a constant in this term, it's okay. You know. And by the way, notice what else we don't have. We don't have any x's. Okay, and that's okay too. So this would be a second order ordinary differential equation written in one of those two, either with the y or without the y, normal form. Okay. Now, we'll talk about classification by linearity. How are we doing on time?
7 minutes.
Say again?
7 minutes.
7 minutes ago. Let's see what we can get done here. Okay. I think I'll start with on a new page. Classification by linearity. An nth order, they start with the order on this one, ordinary, that's your type, differential equation. Now, when I write it, I'm just going to start abbreviating. Differential equation is always going to be DE. Okay? This form is said to be linear okay, if the F, now this is your capital F there, but you write everything on one side, 0 on the other side. If that capital F is linear in every rendition of y, in y prime, in y double prime. I'm sorry, I didn't write that very well. And we'll keep trucking until we get up to y, the nth derivative of y. Okay, now what does that mean? That means every rendition of y, whether it's y or some derivative of y, none of them can be raised to any power except the first power. Okay? Except the first power. You can't have them in denominators, you can't have them to negatives, you can't have them to fractions, you can't have them to decimals, you can't have them to integers other than 1. Okay. So that's what it means to be linear in all those terms. There's one other thing that knocks out linearity. You can't have a term that multiplies a y times a y triple prime, or any derivative of 1 times any other derivative or the function itself. You can't have those products. Those are not linear. If you have a variable y or any of its derivatives, that must be the only variable or derivative in that term, and none of them can be raised to any power other than the first. So that's what we mean to be linear in each of those terms. Okay. So here is a nth order ordinary differential equation. A sub n as a function of x, dn y dx to the nth, plus a sub n minus 1 as a function of x, d to the n minus first derivative of y with respect to x to the n minus 1, plus a sub n minus 2 of x, d of n minus 2 dx to the n minus 2, plus dot 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 until you go all the way down to your a sub 1 of x dy dx plus a sub 0 of x y is equal to some g of x. Okay. Now that's not in normal form, nor is it in your capital F form. This is one way to express your nth order ordinary differential equation. This happens to be linear. Okay? You can have coefficients that depend on x. Now, this subscript really means nothing except it identifies this is the coefficient function for that derivative. That's why the superscript here matches the subscript here. Same here, same everywhere. Here it is. The first derivative, so a sub 1, the zeroth derivative, in other words, just the function a sub 0. In this rendition, they chose to put function of x on the other side. Notice there are no y's or y derivatives there. Those are all grouped here. Every term has one and only one of them at it, only to the first power, okay? And then all the ones that don't have a y or derivative of y, they're put over here, and those are all functions of x, okay? So this is one way we express a linear, ordinary, nth order differential equation. Okay. Now, how are we doing on time? 3:44. Okay, one more minute. So let me write down these two special cases for that equation. The first of these is a sub 1 of x dy dx plus a sub 0 of x y is equal to g of x. Okay? This is a first order linear ordinary differential equation. First order. Your second order would be a sub 2 of x d2 y dx squared plus a 1 of x dy dx plus a sub 0 of x y is equal to some g of x. That would be your second order. Now, why they say those special ones, I don't know. They're just the ones we're going to work with more than the others. Okay. Now, a couple of characteristics here. The dependent variable y and all its derivatives, y prime, y double prime up to the nth derivative, are all first degree. We already mentioned that. The power of each term involving y is 1. We already said that. The second is the coefficients, a sub x, a sub 1, a sub 0, a sub 1, a sub 2, up to a sub n, of your of your y prime up to y sub n, depend at most on the variable x. These cannot have y dependence in them. That way you would have a nonlinear situation. So you can have coefficients that are constant or just of x, but you can't have any y's in those. Now, that makes it linear. What makes it nonlinear? If any of those rules are broken. If you have a product of y's or y primes, if you have a power of y's or y prime, if you have a coefficient that has x's and y's in it multiplied by 1, yeah, it's not. So a linear ordinary differential equation is simply one that's not linear. A nonlinear is not linear. Okay. Also, you can't have functions such as sine y or e to the y because those are not linear functions. If that y here is a sine y or y squared, anything other than a linear function y is not linear. So we're going to begin next time with example 4. Okay? And we're out of time, right? Okay, sorry about that. Okay. Now, so we'll begin next time with example 4. Let me see if you've got enough homework exercises you can work on. This is a fairly long section. You can do any of the odds 1 through 7, especially if their answers are in the back of the book. Okay? You can do number 9, I think. Let's stop there. We haven't talked about explicit and implicit yet, so we'll stop there. Any of those 1 through 7 and number 9. I think that'll pretty much do it. All right, good deal. Okay, you remember the good news, bad news situation? Second?
For what? For class?
Yeah.
Yeah.
What is it?
Holiday.
Yeah, Monday's a holiday. That's the good news. The bad news is we won't be meeting. Okay, so we won't meet again until next Wednesday. So see you in a week.